Okay, so this is taking place instead of you actually having to come to campus for week 4 discussion because the weather's so crummy and I know the roads are still icy. You're going to watch this video. You're going to work these problems with me. If you have a printer, you can print them off. They're in the quizzes and discussion module. Otherwise, you can just write down the problem statement and work through it. So anytime I need to find internal forces, I'm going to have to draw lots of free body diagrams. And just like a shear and moment diagram, I'm going to have to cut between where I have changes in loads. So you can see it's applied here at B. So if between A and B, it's all going to be the same. So we're going to have free body diagrams. And I call these a cake problem because if you put it up like this and you make the widths different, it looks kind of like a wedding cake, I guess you could say. So free body diagrams. I have 10 kilonewtons. I'm going to have an internal normal force from A to B. I'm going to assume it in tension. I always assume it in tension positive. Sum of forces in the x direction equals 0. They're both going to the left, and I'm saying to the right is positive, so I have negative NAB minus 10 kilonewtons equals 0. So NAB equals, I'm going to take that over to make it positive, negative 10 kilonewtons NAB equals 10 kilonewtons in compression. Okay, and that's important because when I want to find the stress, I'll know that I'm looking at a normal compressive stress. Now we can cut it. You can always pull out your post-it notes, and we're going to have another free body diagram, and this time we have 10 kilonewtons pushing in. We have 6 kilonewtons going in that direction, and I have a normal force from B to C. Remember, we also could have shear and bending moment and torsion, but because we have just the axial load, we know that the shear is 0 and our moment is 0 because it's all going right through the centroid. Sum forces, x direction equals 0. Negative NBC plus 6 minus 10 equals 0. Okay, I'm assuming it's in tension, but directionally for equilibrium, to the right is positive. Take that over, add a positive to both sides, NBC equals negative 4 kilonewtons. NBC equals 4 kilonewtons in compression. Move our post-it note. Just like so, between C and D, draw another free body diagram. We have 10 kilonewtons going to the left. We have 6 going to the right. We have 2 going to the left. We have an internal normal from C to D that I'm assuming is in tension. It is pulling away. I'm going to sum forces in the x direction. Negative NCD minus 2 plus 6 minus 10 equals 0 because I'm calling to the right positive. Add an NCD to both sides, and I'm going to have negative 12 plus 6, so I have negative 6 kilonewtons, which is 6 kilonewtons in compression. Okay, either way is fine. And then, I'm going to cut it right here. And I have the option of drawing this big, and when I do that, I'm going to have negative 10, 11, 12, negative 12 plus 11, so I'm going to end up with a negative 1. Okay, I can look at that. It's just like looking at a shear. I'm going to have internal. I'm going to end up with a normal from D to F equals negative 1 kilonewtons. And I can check that because I know that I have to have a reaction at the wall. Okay, Fx. I could also have Fy and a moment at F because it is fixed, but again, all of my forces are acting axially through the centroid, so I know that these are 0. Okay, so if I sum forces in the x direction, I'm going to have Fx plus 5 minus 2 plus 6 minus 10 equals 0. So Fx equals, take all these over, negative 5 plus 2, negative 6 plus 10. Okay, so f of x equals 12 minus 11 is a positive 1 kilonewton, which means I assumed it correctly to the right. And so if I cut it and look at this little nub in this direction, I have a reaction of 1 kilonewton pushing. I can obviously see that internal, I've got to have 1 kilonewton, and it's in compression. So I get the same way whether I cut it and look at this side or I cut it and look at this side. But you remember, you always have to have a reaction there, always, always, always. And you have to include every single force. You don't just like pull something out. So now I can draw a normal force diagram. It is a normal force diagram. Up here is positive, down here is negative, so I have tension and compression, and I have a -1. And then what happens? I have a -6, and then I had a -4, and then I had a ginormous -10. So I can see it's all in compression as it's below that 0, and I'm signifying it's my normal force. If I knew the cross-sectional area, I could come back and draw a stress diagram. We can see that all of them are negative, so my stress diagram would be, down here on the bottom, and it would just be that force divided by area, okay? So this time it says if each of the nails has a diameter of 4 millimeters and can withstand an average shear stress of 60 megapascals, determine the maximum allowable force P that can be applied to the board. Well, I'm hoping you guys have gone back and watched the video on shear stress, okay? Shear stress caused by a normal force. You all need to go back and watch lecture 1.5. Okay, we've missed school Monday, we've missed school Wednesday. I have a feeling next week we're going to be out for the majority of the week, and my guess is they're going to tell us educate from home because we can do that. So if I'm pulling this force P, then this board is going to have a normal stress of P over A because this force is perpendicular. Do you see how that force is perpendicular to the cross section? Okay, as I'm pulling on this board, I have these nails or these bolts that are going through, and so they are resisting, they would be transferring, but they are resisting this force P as well. Okay, and so when I look at the bottom of those, of it going through, I can see there's P and here's that shear force. And now instead of a normal force that's perpendicular, I'm calling it V, and V is shear, okay, because it is running parallel to the cross section of my nails. Okay, so normal force is a sigma, and it is a normal force divided by area. This shear force is tau, and it is caused by a shear force over area. That shear force is coming from an axial load. Okay, it just comes down to free body diagrams. If I cut the wood right there, so here's my wood piece. If I'm pulling P, I can visually see that that inside is going to have a normal force in tension. Okay, as this force is being transferred through, we can see it is going to be trying to cut through a bolt, just like we're cutting through a piece of bread. So shear stress equals V over A. And in this case, V is going to equal P, okay? Because I can use statics, and if we go all the way back to the bolts, pretend the bolts are here now, that resisting shear stress that's trying to cut through the bolts has to be the same as P. So shear stress is V over A. In this case, because of equilibrium, P equals V. Okay, it's a normal force that's now acting as a normal force over the bolts. My allowable shear stress is 60 megapascals. 60 times 10 to the 6 Newton per meter squared. So I put it in pascals times 10 to the 6, and then I go ahead and write Newton per meter squared so I can keep up with my units. I don't know P, but I know my areas. In this case, I have 3 nails with a diameter of 4 millimeters. So I have 3 nails. So I've increased my area. If I just had 1 nail, it would be, 1. But I have 3. So I have 3 areas. Okay? Pi over 4, 0.004 meters squared. And it's not pi over 4, all of that squared. It's pi over 4 d squared. Here's my diameter in terms of meters. If I work this out, then I get a value, and I had to write it down over here because my calculator is no longer working and we are having some technical difficulties with working a regular calculator. And I get 2.26 kilonewtons. I actually got a really long number, and I just moved it over 3 places, okay, and called it kilonewtons. So that would be the maximum load P based on the shear stress of the nail, okay? Shear is tau, sigma is normal, and it is the force perpendicular to the area, or parallel to the area. Normal, shear. Normal stress, shear stress.